So let's solve the second exercise. We have to compute two integrals over the curve gamma. So let's first see what the curve gamma is. It's the anti-clockwise circle center at the point 1 plus 2i with radius 2. So if we have here the origin, then the point z0 is here. And so we have radius 2, so we have circle like this. Okay, so let's call this disk D1 plus 2i 2. So this gamma is anti-clockwise, so gamma goes in this direction. And the idea to solve the exercise is to use the theorem of Cauchy. So let me recall briefly what the theorem says. So if we have f a function from u to c, where u is a region containing the disk, and if we know that f is holomorphic, then the integral over gamma of f dz is equal to 0. So this is first version of Cauchy theorem. Second version, more general, tells us that if now, let's say, A is a complex number lying in the disk, the interior of the disk, so it's called the interior of the disk I gamma, then I can express the kth derivative of f at A as k factorial over 2 pi I times the integral over gamma of f z dz over z minus A to the k plus 1. So I want to use these two results and see in which of the cases we are in the first case or in the second case. So basically, I want to study if these functions here are holomorphic in the inside of the disk. So let's start with the first case. So this is the case, let's say 1, this is case 2. So for case 1, we have the logarithm. So this is the principal branch. And the logarithm is defined over the complex numbers minus the negative real axis. And it goes to the complex number was imaginary part is between minus pi and pi. So this means that this region here is the complement of this red line. So we see that the logarithm is holomorphic on the disk. And then we divide by z minus 4. And here we see that 4 lies outside the disk. So 4 is somewhere here. If you want to do this properly, then you should compute z0 minus 4, the norm. This is equal to 1 plus 2i minus 4. This is 3 plus 2i, the norm. And this is clearly now bigger than 2. But because this is 9 plus 4 square root, this is square root of 13, is bigger than 2. So this means that 4 is not in the disk. And from this, we see that then also 1 over z minus 4 to the power of 2 is holomorphic. So this implies that f equal to log of z divided by z minus 4 squared is holomorphic on the or maybe more precisely on C minus the negative real axis and then also minus the number 4. But this contains now the disk. So we can apply, we apply the first formula, call it star, and find that the first integral is equal to 0. Okay, so this solves the first integral. Now let's look at the second one. Here we see that the numerator is clearly holomorphic in C. And to see what happens to the denominator, we have to locate the numbers 2i and 3 with respect to the disk. So where is now here 2i? So 2i lies here. And 3 lies here. Okay, so we see that one of them lies inside the disk and one outside the disk. So this means that this function here will not be holomorphic. So let's see what does this mean. So this means that the function f defined by x of z squared plus 1 divided by z minus 3, this function here is holomorphic on C septa 3, and this contains the disk. And then this follows because since the distance between 1 plus 2i and 3 is bigger than 2. Now you can check this very easily. And now the other thing, then since 2i belongs to the interior of the disk, for this you just have to check that 1 plus 2i minus 2i is less than 2. And this is clear because this is equal to 1. Then we apply the second formula. Where is it? Here. And what is k in this case? So here we see that we have here above 2, so k must be equal to 1. Okay, and then what we get that the first derivative at the point 2i is equal to 1 factorial divided by 2 pi I. And here we have the integral of the function f z dz over z minus 2i squared, which is exactly the number we wanted to compute. So in order to find the value of the integral, we just need to find what is f prime of 2i. So the function f is written above. So what is f prime? So here we have a quotient. So we have z minus 3 squared. And then we have to differentiate the function above. So this is an exponential. We use the chain rule. Exponential of z squared plus 1 times 2z times z minus 3. And then we have exponential of z squared plus 1 times the derivative of the denominator, which is 1. Okay, so we can rewrite this as x z squared plus 1 times, what do we have above? 2z, z minus 3 minus 1 divided by z minus 3 squared. So now we can substitute z equal to 3. Sorry, z equal to 2i. And we find f prime of 2i is equal to the exponential of 2i squared plus 1 times 2 times 2i minus 3 minus 1, 2i minus 3 squared. So here we have the exponential of 2i squared, that is minus 4, so of minus 3. And now here we have 4i times 2i. And this is minus 8. And then minus 12i minus 1. And then below we have minus 4 plus 9, and then minus 12i. So let me write this again. So this is 5 minus 12i. And then above we have minus 9 minus 12i. Now, so maybe I can just change all the signs. We get something like this. And now we want to bring this normal form. We want to get rid of the denominator. So we take, multiply both by the conjugate of minus 5 plus 12i. And we get below 25 plus 144. And above we get 9 plus 12i times minus 5 minus 12i. $169. And what do we have above? We have minus 45. Then we have minus 108i minus 60i, and then plus 144. So here we see that we get 99 minus 168i. This hopefully is the correct answer if we did all the computations right. So here, the important part was to check the hypothesis of Cauchy's theorem and to check if the functions we have inside the integrals, they are holomorphic on this disk. And so for this, we need to check, we need to know where the logarithm is defined. So we know that it's defined in the complement of the line. And then we need to determine if the points 4, 2i, and 3 are inside or outside the disk.